So today we'll just be talking about independent random variables, covariance, and correlation. So we say the random variables x1, x2, all the way to xn are independent if the joint CDF is equal to the product of the marginal CDFs for all little x1, little x2, all the way to little xn. Now, just be careful with our definition here, right? Because we need it for all, right? For all the little x1, x2, etc. So if you want to prove dependence, not independence, dependence, you just need to find one case that breaks, this formula. But to prove independence, right, you need to show it for every case. So these next two definitions here, right, they just follow directly from the definition of the CDF, right? From this first part about the CDF here, as the CDF property holds for both the discrete and continuous cases, obviously, right? So yeah, most of the time, you'll just be dealing with two random variables that are independent of each other. But it's really important to remember to check the product of all the CDFs, PDFs or PMFs, against your joint distribution, right? To see if the random variables are independent or not. You can't just check one. So you should still know that sometimes, right, you don't really need these formulas. As in both examples of our joint distributions video last time, we know that they are dependent, right? Because in the discrete case, it's clear that the sum of two dice is dependent on the maximum of the two dice, right? Just like in the continuous case, it was clear that since our range said that y must be less than x, we know at least y depends on x, right? So, this last guy, just before we move on here, this guy just states that the independence propagates through functions of random variables, right? So if you have two random variables that are independent and you take a function of them, then the function of the random variables is also independent. And you might be able to prove this using the definition of a function, but really you could just make an intuitive argument here. So I'm just going to ask you to consider, before we move on, what it means for two variables to be dependent. We already kind of touched on that, but just consider what it would mean if we could measure how they were dependent on each other and how much they were dependent on each other. So that's what we're getting to right now. The covariance of any two random variables, x and y, is defined as follows, right? Where it is the expectation of the product of the two random variables minus the product of the expectations of the two random variables, right? So that's a bit weird, but it's this guy right here, right? Where this equality follows directly from the linearity properties of expectation, right? You just expand this out and you'll get this guy. And it's just a fun algebraic exercise. It's really not that hard. But, this is really the OG. This is the real definition, but this is the one you'll be using, right? Now, from this second guy here, you might have just seen, okay, right? I can just use my law of the unconscious statistician, my LOTUS. And now I can find the covariance easily by, calculating both expectations, these guys separately, and then, double integrating or summing over xy times the joint PDF or PMF to get this guy right here. And yeah, that's true. You can do that, and you will do that. But I really do think it's important to know kind of, what this means. So if we look at these three graphs here, you'll see that a positive covariance, right? It just means that, right, our two variables tend to move in the same direction. And then, so as x increases, y increases, right? And a negative covariance means that the two variables tend to move in the opposite direction, right? That's pretty obvious here. And then a zero covariance, maybe this isn't a perfect graph, but essentially it means that they have no linear relationship, right? But as I'll show you in a later, right, this covariance doesn't tell us the whole story, because one of my questions earlier was, how much do they depend on each other, right? So if I change the units of x and y, then the covariance will change as well. So it's not very good to compare, covariance of x and y and covariance of z and w or whatever. So the next slide, I'm going to show you how to measure the strength of the linear relationship between two random variables, and you won't have to worry about the units of the random variables. So the correlation coefficient rho is defined as the covariance of xy divided by the square root of the product of the variances of x and y. This guy right here, right? Where the variance of x and y obviously is non-zero, as if the variance of x or y is 0, then the correlation coefficient, we just define it as 0. So that's this limit here. So as we know from the last slide, right, the reason we care about rho is just because it makes it easier to compare the strength of linear relationships. And since the definition is pretty standard, right, you know all these terms already, I'm just going to point out some important things using these graphs here. So firstly, notice that rho is not the slope of the line in the scatter plot. So it might seem a bit weird, but for example, both of these guys here, right, have rho equal to 1. And this guy has rho -1. You know, upwards, downwards, right? That's where my negative comes from. But remember, like, these guys both have 1, but they have totally different slopes, right? So rho xy is only 1 or -1 if I can write y as some linear function of x, right? So that's the most correlated we can be if we are a linear function of x, if y is a linear function of x. And, you know, that's the most correlated we can be because look, check our range here, right? Either we're at -1 or 1. That's like the two extremes. And you'll notice, this is the second point here, right? You'll notice by looking at this circle graph, this guy, that it's not really clear, it's not true that having zero correlation means there's no relationship between x and y. So keep that in mind, right? So here we have zero correlation, we have no linear relationship, right? But there's clearly a relationship between our x and y. And here it's the same thing. This is also correlation 0. It's a bit strange, but think about that intuitively for a moment and you'll figure that out in a second. Now, this graph here, this guy, is just, you know, this example of negative correlation that's pretty close to linear. Let's say maybe -0.8. And this is like more realistic to the type of things you'll see on a test. And finally, you know, this is pretty standard. Just a reminder here that correlation doesn't equal causation. You know, as my stats prof says, sunburned people tend to buy more ice cream, right? But it's pretty clear that that's just because people buy ice cream when the sun's out, right? It's not because being sunburned means you like ice cream. So I can see, you know, just take a moment here. I can see how first this slide is a bit intimidating, right? But if we just look at these one by one, you'll see the intuition is pretty clear and, you know, all the proofs are mostly algebraic, right? So this first property, it makes a lot of sense, right? Because obviously the covariance of one variable, x in this case, is the variance, right? And, you know, if you plug your x in, you'll see that that's true. And similarly, right, since our rho would be just var x, right, by this part, over the square root of var x times var x, which is var x squared, you know, that's why we get 1, right? Because square root of var x squared is var x. So that's pretty standard there. And then this guy here, this guy is significantly more important, right? When I was talking in the last two slides about changes of units and stuff, that's really this one here, this second guy. So while I do leave this proof as an exercise, right, you should be able to do this from the definitions in this video. But just looking at the intuition here, right, think about how this might be related to the squared, like the squared in front of variance, when we do the linear transformations of variance. So this guy, you know, follows pretty closely from the direction of covariance and, you know, down the line, variance and expectation. And this guy, of course, follows pretty closely from covariance and my variance squared. So this is a really valuable exercise to do here. But if you don't want to do it, you can just memorize this. Now, our third guy is also pretty standard algebraic manipulation. So I'm gonna skip over that guy and look at these next two here. You should remember this, or at least, you know, try to prove it in the next slide here. So number 4, right? We're just providing a formula for the variance of the sum of two random variables. And, you know, this is just to generalize it for any linear thing. So if this looks complicated at first, just remember the linearity properties of variance, right? You're used to these guys. So see how similar this is, that we're just bringing out our a squared, our b squared. And this term here, you know, 2ab, like this is pretty OG stuff right here. So if you think of the covariance as the expectation of product x and y minus the product of expectation of x and the expectation of y, you know, that's like our second definition of covariance. It'll really help you too when you try to prove this guy. So our fifth guy, number 5 here, is a pretty large source of confusion. So I will be proving this one just quickly here. Essentially, we know that if we are independent, the expectation of the product of x and y minus the product of the expectation of x and the expectation of y is 0. Or, in other words, both of these terms, these guys, have to be equal to each other. And this is just because if we do this sum of this sum is just the expectation of x and y. And there's a very similar proof for the continuous case. It's just with double integrals. It might actually be a bit easier, so I'm doing this part here, but this follows, this equality here, the fact that this is equal to this, comes directly from the definition of independence, right? So once you have this guy here, you just need to reorder your sum, which is like just move terms around, and then you have the expectation of x times the expectation of y. So, that part's pretty straightforward, and no one really gets confused about that, but this is what you really have to remember. The converse, the other direction, is not true. So when covariance is 0 or correlation coefficient is 0, we don't know that we're independent. And intuitively, you can remember the example on the last slide of our circular graph, right? Clearly, the x and y in that graph are not independent, right? As if we're off the circle, we know that the other variable is 0, etc. But we did have a covariance of 0. So we are dependent and we still have a covariance of 0 because we have no linear relationship. So, if there's anything on this slide, especially the last part there, that's confusing, just pause the video here and take your time. Most of these things are exercised in the next slide. That will definitely help clear that up. Yeah, so as promised, I've provided some practice problems of varying difficulty here, and I do really highly encourage you to give these a shot. And if you can only do, let's say 2 problems here, right? I would do number 3 and number 4. This one's pretty fun, but, these guys actually matter on the test. But yeah, anyways, thanks for listening. Feel free to ask any questions in the comments below, and please do let me know if I made any mistakes at any point in this video or if anything was unclear. And yeah, I'll see you guys next time.